Hi folks, today we're going to talk about the cubic and cube root parent functions again, but today we're going to focus on the attributes of those functions, kind of the key features. And we started talking about that a little bit at the end of the notes yesterday. We talked about the vertex, we talked about the intercepts, the domain, the range. We even talked about end behavior, which was a new thing for us. But today our conversation is going to solely focus on key attributes, some of which we discussed yesterday, some of which we haven't talked about yet at all. So we're going to start with the cubic parent function. The equation is f of x equals x cubed, or y equals x cubed. Yesterday we talked about how the domain is all real numbers. We talked about how the range is also all real numbers. We don't have any boundaries on our cubic parent function. We talked about how there was exactly one y-intercept and exactly one x-intercept, and those occurred right here. So that was the origin. These are all from our conversations yesterday. And finally, we have an attribute that we haven't discussed yet, and it's that the graph of a cubic parent function has rotational symmetry about a point. Now, rotational symmetry is something that you're not quite familiar with. The point that it rotates around is the origin. And so what I'd like to do is show you kind of a little, not animation, but kind of what that is supposed to look like whenever you have rotational symmetry. So I'm going to pull up, there we go. This is Paint 3D. This is a picture of the parent function. And so what I've done is I've selected the entire function and I'm going to rotate it. You can't really see, but above there's a rotation button, and I'm going to rotate this. Try to rotate this. There we go. I'm going to rotate this around. So as I rotate, you can see the degrees that I'm rotating in the center. And if I rotate 180 degrees, look at the picture. Other than the numbers that mark the right, left, bottom, and top of the x and y axis, other than those numbers, the shape of the graph, how does it look? It looks exactly the same. And that's what rotational symmetry is. Whenever you rotate your graph 180 degrees, it should look exactly the same as it did before you rotated. Now, the one point that stayed the same, stayed exactly where it was the entire time, was the center of rotation. And here I've got that circled. That is the origin. So watch again. If I rotate 180 degrees, my origin stays exactly where it is. That's the center of rotation. And I end up with my graph again. So this is what rotational symmetry looks like. It's easier to spin your graph on paper, like put your pencil on the origin and spin paper. But since we're virtual this year, it's kind of hard to do that. So I wanted to show you that little animation. So what is symmetry? Well, we've talked about rotational symmetry, and we've discussed symmetry in the past. Symmetry is when one shape becomes exactly like another if you flip it, slide it, or turn it. So specifically, rotational symmetry about a point means if you rotate a graph, (180 degrees, so halfway to a full rotation, halfway to a full turn. If you rotate a graph 180 degrees around a point, the graph should coincide with itself. It should be the same as it was before you rotated it. So the graph should coincide So kind of fall right on top of in the same place, should coincide with itself. Oops. There we go. So just kind of a brief overview of symmetry and talking about what rotational symmetry truly is. Let's go back to this parent function. Is there a maximum or a minimum y value? Well, we've got an arrow here, so there's no minimum. We've got an arrow here, so there's no maximum, so the answer is no. There's not. But if you restrict the domain, what that means is that you're only considering maybe the domain from -1 to 1. Only from here to here, and all this other stuff doesn't matter. So we're just talking about this stuff in the middle. Well then, yeah, there's a minimum value right here. There's a maximum value right here. And so if you restrict the domain, then yes, you do have maximum and minimum values because you don't have arrows that continue on for forever. You have boundaries. So what I'd like to know, first of all, I'd like to erase this. See how easy that is. That's nice. What I'd like to know is what is the maximum and minimum values of y equals x cubed, the graph that we have, on the interval from -1 to 4. So remember, these intervals, these are x values. So I'm going to go look for -1. Here's -1. Here's my boundary. Everything before that, I don't care about. And then 4 is my other boundary. So I'm going to put my boundary here. Everything over here, I don't care about. All I care about is this stuff in the middle from here all the way to wherever it crosses on this boundary. So let's talk about the minimum. The minimum is easy to see. The minimum is down here. And you can either pick it out from the graph or you can do it algebraically. So if the equation is y equals x cubed and the minimum value is -1, then you can substitute -1 for x and you get a minimum value of -1. So it's lucky that there's an algebraic way to do this, because if you look at the graph, there is no way for this graph to show us the maximum value because it's too high. So what I'm going to do is go ahead and use my algebra. So I'm going to take my equation, y equals x cubed. I'm going to substitute the x value, the biggest x value, so that's 4. Well, what is 4 cubed? 4 times 4 times 4. That's 16 times 4. That's 64. It's the maximum, the biggest number, if you restrict the domain. So we are simply substituting those values. If -1 is the smallest number, I substitute it here to get the minimum. If 4 is the biggest number on my interval, I substitute it for x, and I get my biggest number, my maximum. So the next question doesn't have a graph, and we're expected to do this algebraically. It asks, what is the x-intercept? Let's move this up a little bit. What is the x-intercept for f of x equals x cubed plus 125? It's definitely a cubic function, but it's not the parent function because we have this plus 125 here. So if I want the x-intercept, think about what that looks like. Looks like an x value. And what do we have for the y value? We have 0. An x-intercept is always an x value, comma 0. So I'm going to take that 0 and I'm going to substitute it for y. I have 0 equals x cubed plus 125. So I've got an equation. It has one variable. I can solve this, but it looks a little weird. So if I'm going to isolate x, think about your algebra training. you're going to move the constant. So 125 minus 125 becomes 0. You have negative 125 equals x cubed. And you don't want x cubed, you just want x. So how do you uncube a term? Well, yesterday we had a conversation about the cubic and cube root parent functions, and we've discovered they were inverses of each other, which means that cubing and cube rooting are also inverses of each other. If I cube root both sides, I can eliminate that cube, and I can get x equals the cube root of negative 125. You can use a calculator, but I know that if my cube root is of something negative, then my answer will be negative. And 5 times 5 is 25, times another 5 is 125. So my x value is negative 5, and my x-intercept is negative 5, 0. So algebraically, without a graph, without a picture, this is it. So let's look at the y-intercept. I want the y-intercept for this graph. Again, I know it's a cubic, but I know that it's not the parent function because it has a minus 8 in there. My y-intercept, think about the way that it's formed. It's the y value when x is what? 0. So what do you do with 0? Is it an x value or is it a y value? It's an x value. So you're going to put it here for x. We have y equals 0 minus 8 cubed. 0 minus 8 is negative 8. And if you cube it, negative 8 times negative 8 is 64. And 64 times another negative 8, you can use a calculator, is negative 512. So my y-intercept is 0, negative 512. Now finally in this page of our notes, before we move on to the cube root parent function, it asks a basic question that you are going to be expected to know how to do. It asks what the inverse is of y equals x cubed. And we already know that the inverse is y equals the cube root of x, but we need to show our work. And so in order to do that, let's go back to 2 problems before where we were asked to find the x-intercept, and we undid a cube by cube rooting. So let's try that. Let's solve and find the inverse of y equals x cubed. So remember, the inverse means that we need to switch x and y. And we need to solve for our new y. So the opposite of cubing is cube rooting. So I'm going to cube root both sides. If you cube root a cube, that cancels out. You have just a y by itself, and you're left with the cube root of x. So this is the inverse. And we can write this as the inverse function, the cube root of x. So just a little notation from before break. Looks like we have a power of -1, but it really means the inverse. So let's use that knowledge, and let's move on down to the second page, which focuses on the cube root parent function. Very similar, but slightly different. In the cube root parent function, the domain, still all real numbers. The range, still all real numbers. These are topics of conversation from yesterday. There's exactly one y-intercept and x-intercept at the origin. And it turns out that the graph also has rotational symmetry about the point 0, 0. If you were to take it and rotate it, the origin would stay exactly where it is, but the new graph would coincide with the old graph before you rotate. So let's talk about the minimum and maximum values of the cube root parent function. Now, I have an arrow and an arrow, so I don't really have maximum or minimum values until I restrict, until I give the graph an interval. So if I give an interval from -5 to 2, remember these are x values. On the graph, -5 is 1, 2, 3, 4, 5 right here. So we ignore everything outside of the interval. And 2 is right, where is it? Here. So we ignore everything outside. We're only concerned about this stuff that is inside of the interval. Now notice that those 2 points don't really have nice, clean, ordered pairs. And so we're definitely going to have to do this algebraically. My equation is y equals the cube root of x. If I take my minimum interval value, -5, and if I substitute that, I get something that I can't really evaluate without a calculator. If you type the cube root of -5 into the calculator, you're going to get -1.7 something something something. So we don't really get a nice pretty number, but I did type it into a cube root calculator, ignore the stuff that's on the sides. It was a quick Google search, and so I was able to type it in and get about -1.7. So this is how we say about, -1.7. That's the minimum. So if I do the same thing to calculate the maximum, I'm going to need to use the larger interval value. So the cube root of 2. Well, when I type in the cube root of 2 into a cube root calculator, I end up getting, let me change this to about instead of equals. So the symbol for about is almost like a wavy equal sign, almost looks like bacon. So it's about 1.3, and that's the maximum. And you can do a quick spot check to make sure that it kind of makes sense, because if your minimum is bigger than your maximum, then you know you did something wrong, because by definition, minimum means the smallest value. So we're just taking our x values and we're substituting them into the equation. Now finally, our last question today says, what is the y-intercept? So 0, comma something. What is the y-intercept for f of x equals the cube root of x plus 81? So it's a cube root function. It's not the parent function because it has the 81. So I'm going to find the value of y when x is 0. So I have the cube root of 0 plus 81. Well, 0 plus 81 is just 81. And what times itself 3 times gives you 81? Well, there's not really a nice pretty answer. So if you try to cube root 81 in a calculator, you're not going to get an exact answer. You're going to get an approximate answer, a decimal. So here we are going to use our about symbol, and it's about 4.3. So our y-intercept is about 4.3 for the y value, 0 for the x value.